Okay, D block, this is your 5.1 lecture. Polynomials. Polynomials, I've given you an example here. Poly for many terms, okay? So we can have many terms. We're only going to have one variable, okay, when we study these. And the thing to remember, though, is that all of the exponents are whole numbers, okay? So what you can't have then, whole number exponents. So let's give you a couple examples what would not be a polynomial, and that would be anything with square root of x, because that's the same as having a rational exponent, a fractional exponent, so that's not allowed. And you're not allowed to have anything with 1 over x, so no x's or variables in the denominators, because that would be like having a negative exponent. Okay, so only your whole number exponents, that's the rule to make it a polynomial. Okay, let's talk about the degree of a polynomial. Here's a vocabulary question I could ask an easy short answer. The degree is the value of the highest exponent. So if I look at the example that I gave you, then right here the highest exponent, is a 4. So this degree, we're going to call it n, is equal to 4. Okay? So that's a degree. And we also have a leading coefficient. And I would say that is the number in front of the highest exponent, okay? So leading coefficient, let's go here. I'm going to use the 5, but I'm going to pick up the negative as well. So I'm going to say -5 for my leading coefficient. And then there's a constant term. We may have already done this a long time ago, but this is a good reminder. The constant term is the number with no exponent at all, and so that, of course, is your 8. Okay, and I also want to point out one thing. We have what's called a standard form. So maybe I can fit it on here. And actually, when things are in a standard form, it's a lot easier to find degree and leading coefficient. So a standard form, I'll point out, is decreasing powers of x. Okay, so let's see if we can write this one in a decreasing powers. I'd start with the -5x to the 4th, and then add my, -7x cubed, and finally I have my 3x squared, and plus 8. So that would be a standard form, where I have the exponents in a decreasing order. Okay, so I've gone ahead and I've drawn a few graphs of some typical polynomials. Okay, and you'll notice they're smooth, they're continuous, no holes, jumps or gaps, no pointies. They may have a little wiggles going around here and there, and they tend not to be symmetric. Okay, so but what can we look at about these graphs? And the first thing we're going to look at is end behavior. Okay, so end behavior is basically which way are the arrows going on either end of the graph. So if you look here and here, you say which way are the arrows going? Well, they're going up, okay? They can go up or they can go down. Okay, I know they're going left and right, that's a given, but are they going up or down? So when I ask the question, what's the end behavior? The answer to this first one would be left is going up and the right is also going up. Okay, so that's a good answer for that end behavior. That's all you have to say. Then the next one, we could look at that one and say, okay, what's the end behavior? Well, this one is left, but it's heading down. I look at the other one on the right, and it's going up. So different end behavior than the one before. Okay, and we're just going to keep going. If I look at this one, I have a left is up. Whoop, I hope you caught that, because obviously the left is down. There's the left going down. Looking at the right, that's obviously going up. Alright, and the last one, it's filling out the chart. The end behavior would be left is down, and the right is also down. So, you know what you could do? Let me try this. If I erase all this, you could, don't have to, but you could write both down. And that would be an acceptable answer for in behavior. Now, that's one thing we can talk about. Let's talk about something else. Another thing we can talk about is what's called a turning point, okay? A turning point is a place on the graph where it changes from increasing to decreasing, or from decreasing to increasing. Now remember, we always do this from left to right, so I'd look at this first one and I'd say, okay, that's decreasing, and then over here, that's increasing. So right there is a turning point. There's a turning point, and there's a turning point. Okay? So how many altogether, I could ask you? This one has 3 turning points. This one, let's see, right about there, has 2 turning points. What about this next one? When you look at this next one, you're kind of following along the graph. I'm increasing in the y. The y values are increasing. I'm increasing, and it never decreases. So that would be 0 turning points. And then this last one, of course, would be increasing, and then it's decreasing. So that would be 1 turning point. Okay? And what's interesting is we can tell this about polynomials without even having to look at the graph. Okay? So we'll talk about turning points in a minute. I want to get back. I forgot to talk about intervals of increasing and decreasing. So intervals. And let's do decreasing because I am running out of room. Intervals of decreasing. To do an interval of decreasing, you'd have to have some values on your graph. So let me fill in a couple of these. So let's say this one's at -2, -3. And this one here, decreasing is, maybe that's 1, 4. And then we'll call this +2, +3. Alright, so there are some points on that graph. And I'm going to talk about the intervals of decreasing. If you remember intervals, we always go x values, okay? So let me say x values, because that's going to be true for all of them. Don't forget. It's always got to be the x values. And you go from left to right. So left to right. Those are the rules. Alright, so let's identify some interval of decreasing for the first one. In the first one, it decreases, you know, at the very left, it's decreasing all the way till it gets to that point. So I would say from -infinity until it gets to here. And you remember, you're doing the x values, so you're going until -2. Do not include the -2, okay, because it's actually flat. As it turns around, it has to go through flat, which is neither increasing nor decreasing. And let me get rid of this line so I can do and in decreasing on another interval, because it's also decreasing from, you know, these 2 points, between those 2 points right there. So that would be from x is 1 until x is 2. Okay, so those are my intervals of decreasing. Okay, and we'll practice some more of that as well. Okay, now I promise you we'd be able to tell things about the graph when we're just given the equation for the polynomial. So going back to my example, I want to point out this has a degree, in this case, of 4. That's the degree. The leading coefficient is a -5. Okay, that's sort of the important information to get out of this. So, what you can do, let's talk about turning points first. The number, I have to start with max, the maximum number of turning points. Is always equal to the degree of the polynomial minus 1. So there's sort of a formula, not a formula, but a rule that you need to remember. So in the case of this problem that we have over here, I have 3 maximum turning points. So that's not hard. And after a while of doing this, it sort of makes sense and it won't be hard to remember. 3 maximum turning points, and it turns out these come in pairs, okay? So it's possible you could have one turning point. Okay, so 3 or 1. Okay, and 3 is the maximum, and that's the rule you want to remember. The other thing to remember is end behavior, and how do we tell that from just this equation of the polynomial? And here things are more like 4 options are possible. So this is not a graph that I'm trying to draw with an x and y axis. I'm just trying to divide like 4 different scenarios. There are 2 of the scenarios that have even degrees. Okay, and then the other option is to be an odd degree. Okay, then there are 2 things that could happen with the leading coefficient. You could have a leading coefficient that is positive, or you could have a leading coefficient that is negative. Okay, and so every combination of these options will give us our 4 different outcomes. So let's take a look at these 4 outcomes. Considering first the even degree leading coefficient is positive. Well, actually, I can remember one that we've studied quite well in the past, and we know it like the back of our hands already, and that would be x squared. Okay, so anything that has an even degree and leading coefficient of positive will look a lot like x squared when we're talking about, remember, this is describing end behavior. So here are the rules for just that. Now, remember, when you're talking about end behavior, we don't know what's going on in the middle, okay? The middle is still a mystery, but at least we can tell what the arrows on either end are doing, and that's going to be like x squared. So that would be left up, and, right is also up. Because remember, we usually have a parabola that opens up, okay? Touchdown, Jesus. All right, then let's consider the other one that we're very familiar with, and that's when you have the even degree, so we have an x squared, but the leading coefficient is negative. So this is going to be somebody that looks on the ends, maybe not in the middle, but on the ends, he looks like a negative x squared, and we all know that's a parabola that has been reflected across the x-axis. It's been reflected up and down. So it's opening down now, which means the end behavior would be left is down and the right is down. Or we could say both down. Okay? So these are both up or both down. No big deal. Let's talk about the odd degrees. Excuse me. If you were in class, then we did a lot of graphing on our calculators, and we looked at odd degrees, and they all had those robot arms or disco arms where it comes up one side and down the other. So let me go over here. Just I need a place to draw an x cubed function to remind you what that looks like. So that was an x cubed function. All right, so any odd degree with a leading coefficient that is positive is going to be anything like x cubed. Okay, that certainly fits the requirements. So they'll all have the same end behavior, and that is simply the left is down while the right is up. Okay, so if you can remember what x cubed looks like, you can come up with this end behavior. And then, of course, in the other last final outcome, same idea with an odd degree, but it's been vertically reflected because the leading coefficient is negative. Therefore, all we have to do is reflect this and make the left up and the right down. Okay, so that should make sense. Even degrees, they both go in the same direction. Odd degrees, they go in different directions, and you just got to get up or down on the right sides. Why don't you go ahead and try these next ones? I want you to do 4 things. I want you to identify the degree. I want you to identify the leading coefficient. I want you to identify the maximum number of turning points. And then I want you to describe the end behavior. Pause it if you want a chance. Do it on your own, and then you can check my answers. When I go through this one, the degree is 5 because that's the highest exponent. The leading coefficient is a positive 3, and I'm sort of real explicit to put the positive because I'll need that. The maximum number of turning points would be the degree minus 1, so that would be a 4. And then the end behavior with an odd degree that's positive leading coefficient is going to be left, down, right, up, just like any x cubed or any odd would be without a reflection. And then if I go to this other one, the degree is 6, the leading coefficient negative 7. The maximum number of turning points would be the degree minus 1, 5, and the end behavior, let's see, I'm an even degree, so that means they're both going in the same direction, but it is a negative, so that means they're both down. So I'm just going to write both down. Okay, so that's really all there is to that. Okay, so we want to talk about how could we go about graphing these polynomials, and we're going to do that in the beginning here, just using the end behavior, like we've learned how to do now, and then a table of values to help us understand what's going on in the middle. Okay, so we have the ends by just looking at degree and leading coefficient, and then the table of values for the middle. So if I have a table of values, I just want middle values, so somewhere around the middle. You might want to go out to negative 3 plus 3. You know, I've picked a pretty easy one here. And then we got to figure out the y values. So I'm going to have to figure out y, which is equal to minus x cubed plus 3x. And we learned how to do this on a calculator in class. Okay, so got my table of values, and now I'm going to start the graph. And I'll do that with end behavior first. It is an odd degree. It has a leading coefficient that is negative, so it's going to be left up, and it's going to be right down. Okay, so that's how I mark it on a graph rather than using the words like we had been using. I just draw my arrows in, leaving the middle blank. And then I'm going to put the points in that I know. Negative 2 and 2, negative 1, negative 2, 0, 0, 1, 2, and 2, negative 2. Okay, so there's a lot of zigzag going on in there. So now I can just connect the dots as best I can, going left to right. Oh boy, did I miss that. There we go, that's better. And connecting the arrows and the dots. So that's basically a gist of what the graph would look like. And you will notice it is a third degree. And how many turning points did this one have? If we look at turning points, there's one here, and there's one here, 2. So it did have the maximum number of turning points for this graph. Okay. So this time we want to be able to find the degree if I'm just given a table of values. So this is getting back to, you've collected some data out there in the field, you've done the hard work, and you're staring at the numbers and what are the numbers telling you. So the important thing to do here is when we have a sort of all of the values of x differ by the same amount. Okay, so these are all different by 2. So they all differ. I don't care what that difference is as long as it's the same. So they all differ by the same. And if that's true for x, we're going to look at the differences for y. So in the beginning, we'll look at what's called the first difference. Okay? And see if that's constant. And if that were constant, then we could go do a delta y over delta x. You know, and that's starting to sound a whole lot like a slope, you know? So that would be linear if we could find the first differences were always the same, because the x differences are always the same, so the slope would always be the same. That's a line. Okay, so let's see if we have a line. Let's try this. When I subtract top minus bottom, always do top minus bottom just to keep it straight, it's always the same direction. I'm going to go minus 1 minus a negative 7, so it's minus 1 plus 7, 6. Then I'll take negative 7 plus 3, negative 4 when I take those two. When I take these two, I get a negative 8. Already I can see I do not have the same first difference every time, but I'm going to keep going. 5 minus 11, 11 minus 9, 2. Okay, so obviously I don't have a linear function or polynomial of first degree, so that's not there. So let's keep going and see if we can come up with a second difference and see if it's the same for every consecutive number here. So let's go back here. What is 6 minus a negative 4? 10. Negative 4 plus 8, because I have to subtract the negative 8. 4. And then negative 8 minus a negative 6, which is a negative 8 plus 6, which gives me negative 2. Alright, so these aren't the same either. Negative 6 minus 2, negative 8. Oh boy. So, second difference, that didn't work either. Same, if these had been the same, we said that would have been linear. It turns out if this was the same, this is very much a calculus kind of problem, this would have been a quadratic, or degree is equal to 1, degree is equal to 2, so equal to the number of the difference that is the same. So let's go ahead and look at third difference. Third difference. 10 minus 4 is 6. 4 plus 2 is 6. Negative 2 plus 8 is 6. Bingo! We hit the jackpot. The third difference in the same. This data is a cubic. The degree is equal to 3. Okay? So that's how you find degree. Alright, we'll do more of these in class. I'll see you then.